Computer. Perfect. So this lecture is going to be recorded. Remember, if you're audible, you may be audible in the YouTube. But as a point of fact, actually you won't be. So please remind me to repeat questions that are asked by the live audience. And if you chat or appear on the Zoom world, you will also appear in the YouTube video. I sort of told a fib last week when I said we're sort of done with imperative programming. The second part of today's lecture is going to talk about objects. And at that point, maybe I can say we finished. We still have a couple extra topics to do, namely exceptions and scoping. So this may be a shorter lecture today. I may actually be able to give you a break for once, but we'll see. So let's just go right into exceptions. So let's just talk about Python. So when Python parses a file, it will return a syntax error when the contents of the file do not correspond to Python code. So that's like the first thing that happens when you give Python a file. Python runs through that file and it says, I need to check that this is even genuine Python. And if it's not, if you forgot to put a semicolon somewhere, or if you used an illegal character, you're going to throw a syntax error. Code that passes this stage, that passes parsing, transitions to something called runtime, right? So once Python sees your file and says, yep, that seems like valid Python, I can execute it, it pulls it into RAM, it's running in this interactive mode, and that's called being in runtime. Now, we can also have errors in runtime, which are a little bit different than the parsing errors. If you get a parsing error, nothing happens at all. It just says, go back to your file and fix it. Runtime errors are a little bit worse because they don't occur until you're in runtime, which is kind of bad. Your software is running, and if it comes across an error, everything stops. It aborts. Everything is dumped out of RAM. Anything that you've computed is lost. So this is why sort of runtime errors are significant, right? If you were doing some type of important computation, trying to save a bunch of stuff, you've just lost all of your work. Okay, so here's a little bit of parlance, because today I want to show you how we're going to sort of handle these runtime errors, because it's not possible always to avoid them. So here's the parlance. So we throw errors and we detect them. So to throw an error means to detect an error at runtime and react with a message. So you have some code, you've detected that something has happened that shouldn't happen, oh, we're going to try to divide by 0. We're not allowed to do that. So I can throw a divide by 0 error. To catch an error means to catch the thrown error and to react to it. So there's these two pieces of nomenclature you need: throwing errors and catching errors. Now, to throw an error is easy. I have exactly one slide of that at the end of this lecture. We're going to be mainly focused on catching these errors and handling them somehow. So to repeat myself, today we're going to learn how to catch exceptions so that our programs can continue running even if they encounter these runtime errors, which are significant. So here are some common runtime exceptions. So have any of you seen an assertion error yet? So this is the very common error that you get in the MyPyTutors. So an assertion error, this is actually quite handy. At any given point in your code, you can make an assertion. You can say, I assert that x should be equal to 2 at this point if I've coded everything correctly. And that's actually good coding practice because it helps you catch errors. It just means I'm asserting that two values have to be equal. And the use case for this on your MyPyTutor is that we're just asserting that the answer you're giving to us should be equal to the actual answer. Right? So when you trigger these assertion errors, that just means you've done something wrong on the MyPyTutor. So that's one type of error. I/O error. This is an error we get when we try to open files. So you may get an I/O error if you try to open a file that doesn't exist. You may have triggered this on your assignment 1 if you didn't give Python the correct file path to your file. So this is an example of perhaps an error that we can't detect ahead of time. We don't know that a file doesn't exist until we try to open that file. So here would be a good use case for catching and accepting around it. Index error. This is the error you get when you index out of range on a list. Key error. This is the error you get when you try to index into a dictionary for retrieval at a key that doesn't exist. Name error. This is when you use a variable that hasn't been set yet. Type error. This is when you give an unexpected type to a function. This is an odd thing for me to say because I keep saying sort of Python is not a type system, but there are a few instances where it is looking at types, and I have some examples. And value error, that's when you give a function the correct type, but you've given it an inappropriate value. And again, I have another example to demonstrate this. And finally, zero division error. So this is when you attempt to divide something by 0 and the computer is not able to do that. So these aren't a comprehensive list of errors, but they're the most common, I would say. And in addition to these errors, you can also throw custom errors, which I don't think we really teach you, but you should be aware that you can really have as many errors as you care to sort of create yourself. Okay, so just some very basic examples of how to throw these errors. So what is the first index that doesn't exist in this list? Okay, 3? 3. So if I okay, so that's actually one more. So if I ask for x is at 4, that's certainly going to return an index error. But if I were to also ask for this list at 3, I think 3 is what I wanted here, just to re-emphasize that we're indexing from 0. So don't forget that the indexes in x's are 0, 1, and 2. So the third index would have already triggered a index out of range. So certainly the fourth index also triggers out of range. I'll change that even though it's not incorrect. Key error. This is also obvious. If I say, please go and retrieve me the value that's keyed for B, you're just going to say, sorry, we can't do that. Now, again, I want to emphasize that this isn't a small error when you're coding this. If you do this in your program stops, just terminates. It doesn't do anything else. It's like if you've ever been on your phone and like one of your apps just ceases to run, just disappears. Like what likely has happened in that app is it's thrown some kind of error that it didn't recover. So it's an extremely significant thing. I don't know if you guys get blue screens of death anymore, but back in the Windows era, you get them a lot, and that would indicate the same thing. Okay, so here's what I'm talking about type errors. So plus would be able to operate on 2 integers or 2 strings. So here's a case where I'm saying, can you do 2 plus 2? Would this work in Python? Why not? Yeah, because these are incompatible types to try to add. So that's exactly what Python's going to report here. It's going to say, hey, you gave me a string and you're trying to add something to it. And in fact, the thing you're trying to add to this string is an integer. So you can't concatenate a string to an int. So that's why you're getting a type error. These are the wrong types for this function. Just notice if I permute this, if I say 2, the integer, plus 2, the string, what kind of error are we going to get now? Same error, but what is it going to say? Yeah, it's a little bit different, right? It's still a type error, but it's saying I now can't add a string to an integer. So just noticed here that the ordering sort of mattered, right? When Python read through 2 plus 2, it's sort of parsing. Remember, we're talking about parsing from left to right. And it's saying, oh, there's 2. It's an integer. There's plus. That's still fine. Oh, and here's a string. That's no longer fine. So that's where you get these type errors. So again, I'm only really concerned about this. Right? Everything else over here is basically to help you debug. But if I were to ever ask you, like, what kind of error does this return? If this was like a multiple choice question on your exam, which it very well could be, I would just list all of the errors and not sort of like these explanations. Value error. So note that the integer casting function has this following type contract. You give it a string, and it returns an int. Okay, so if I type int and then the word 10 into Python, does Python detect anything wrong with this? Is this the wrong syntax? Like at this level, before hitting enter, right? Is 10 a string? So this is fine. Like Python goes, yeah, this is fine. I'm the integer function. You need to pass me a string, and I'll return to you an integer. There's nothing that we can really say is wrong with this yet. If in there I put something like a list, it's going to say, hold on, I can't do this. You're giving me a list. Well, that's a bad example because strings are lists. Suppose I gave it a dictionary there. Then it would say, I can't do this. That would be able to be detected at parsing because it says, you know, I'm expecting to get a string, and you're in fact giving me a dictionary. So this is actually what we call a value error. It's the right type. It's a string, but it's in fact not the right value. There is no integer that corresponds to 10, right? So integer was expecting a string that looked like an integer. So just keep in mind that little nuance between when something triggers the wrong type and when something triggers the wrong value. So again, a value error is when you give a function something of the right type, but it in fact was expecting the value of that type to be a little bit different. why do we want to catch errors? Can't we just avoid throwing them? Yes, right? So essentially there would be ways of coding in such a way where we never throw errors. But our code would get like super long, right? So for example, if I wanted to ensure I never opened a file that didn't exist, I could write a bunch of code that says, look to see if the file exists, and if the file doesn't exist, right, just tell the user to try again. That's going to make our code super messy and super long. Now, the Python philosophy, now, I have two sort of philosophies here. I really think that errors should only be used in this case of a runtime error, like when it is absolutely impossible to actually determine that error would occur. I was looking this online, and the Python community sort of says, using errors in your control flow is generally fine. I don't agree with that philosophy, but the Python community finds it okay. So what I'm trying to express here is that it helps simplify your code to throw and catch errors. But we have to be really careful when catching errors because it's a really sort of powerful tool, and it's really easily abused. So generally speaking, we shouldn't cause errors to be thrown. But practically speaking, it's kind of impossible to detect all of these cases, especially when you're interacting with the user. If I have a prompt and I say type in a number, and they type in a name, like that's going to throw an error, right? Unless like I wrote some type of parser to do that type of, to identify that the name that they wrote didn't actually correspond to a number. But now I'm just duplicating a bunch of stuff. So it will be okay. So, but practically speaking, we do need to catch errors because users can be, sort of assholes, right? They're like, people could try to break your software, right? They're not necessarily going to use it in the exact manner that you prescribed, right? Ask any video game developer how easy it would be to develop video games if gamers never tried to break them, right? That's most of what they're trying to account for is all of these edge cases. So here's a new control structure called the try except. Other languages call this the try catch. But in Python, it's called try except. So basically what happens here is that we can try to execute some code where errors may occur. And if an error occurs, particularly exception name, so exception name is going to be one of the names of the errors I showed you at the beginning, it can say, oh, I tried to run this code, but an error occurred. I'm not going to terminate execution, but rather just like call this exception code. So I'll give you an example. But here's the general structure of this new control structure. So this control structure is also called a try-catch. It's actually more commonly called a try-catch. So you should avoid using this function. It should only be used as a last resort or in the user-facing layer of your software. This is what I'm afraid that people will use this for. You write a piece of code, and it's buggy, right? It sometimes fails. And you say, oh, okay, just try to run my buggy code. And if my buggy code fails, then do something else. That is a totally inappropriate way of using a try-catch. And I see it all the time. It's like really tempting, right? So don't use it for those reasons. When you use a try-except, you're sort of obligated to put here like what exact error you are trying to catch for. Yeah. So here's some examples. So here's x equals 0. There's 1 divided by x. So far, Python says this is all fine because 1 divided by x expects to divide integers. 0 is an integer. However, if I execute that, it's going to say, oh, divided by 0, and now the party's over. I can do this instead with a try-catch. So it works something like this. I can say x is equal to 0. Try to divide 1 divided by x. And in the exception that we've divided by 0 in that try, print, please don't divide by 0 instead. So if I were to run this, Python spits out, please don't divide by 0. Right? And there's a big difference between what happened at line 2 and what's happening at line 8. You don't really see this reflected in the REPL because the REPL doesn't dump out. But if you were to write this in like a file and call it into Python, as soon as it hit that 0, like it stops running your program. Right? In the second case, your program still gets to keep going. Right? It said, oh, there is some type of error, but we've handled it, so I'm still waiting for like the next thing. So this really allows us to like avoid errors that would otherwise end the party. So note that we are not obligated to include the exception kind. I have to fix the grammar on that one. We can catch any exception. So I can say x is equal to 0, try. Now I've inserted another error in here, print y, except you did something fishy. So there are two errors that are going to be thrown here. So the first error is going to be a name error because I'm asking you to print y and y doesn't exist. But I'm also I'm also throwing a division by 0 error. So here I could say try to do this following code, and in the case where you detect any errors, print this message. But this is exceptionally bad coding practice. Don't ever do this, right? Always put in the particular error that you're trying to catch, because like suppose you don't put the particular error, like this is just going to hide every mistake now that you've put in your try branch. And that's going to be a disaster if you like put in other, if you've coded in other mistakes that you weren't anticipating to be there. So here's a better way to do it. So we can catch sort of a sequence of errors if you'd like. So I can say something like try to print y and then divide 1 by x. And in the exception that there's a name error, say you're using an undefined name. And if in the exception that there's a 0 division error, print you have divided by 0. Right? So you can you can accept as many singular errors as you please. But in fact, you also don't have to include it, which I'm saying is extremely bad practice. So this is the better practice. You only try and accept over errors that you can specifically name. Like otherwise, it will screw you. Okay, so let's just do some practical stuff. So let's just take a look at this function. And it's a function which takes no inputs and returns an integer. And what I want this function to do is just prompt the user to enter a number. And then once the user successfully enters that number, I want to just return the doubling. So this is going to demonstrate a few things, right? Because like, what's the purpose of having a function that accepts no input? I will show you. Okay, so here, let's just do some coding. So def IO double. It's going to take nothing and return an integer. And we're going to do something like prompt the user for input until user enters a number, or actually an integer, then return double that integer. Okay. So again, we're just going to do this in little pieces. So let's just do this without any error catching. So what do I want to do? I want to say that sort of string x maybe is equal to input enter an integer. And then I want to say like the integer version of x is just me converting this. And then I just want to return integer x and double it. Okay? So notice here, oh, it's maybe too big. There we go. I'm just going to call it into Python. Oh, am I in the wrong directory? Let's check. I am on desktop. Where's this? Desktop. P3 sandbox. There we go. Okay. So notice how I call this function now, because it has no input. So I can just say, like, execute the lines of code in IO double. You don't really need input. So when I hit enter, it's going to give me this prompt. So let's enter an integer. Okay, that's working as expected, right? Okay, so let's do something unexpected. So now I say 10. Boom, right? Error. This is the worst thing that could happen. Okay, so let's fix this now. So where did the error occur? What line did the error occur here? Line 9, right? And what type of error was it? Right, value error. Right, because it's getting a string, but that string is of the wrong value. Right, that integer casting is really expecting to be passed something that looks like an integer. So what should I do in the case where that doesn't work? Yeah, I want to say something like print, that was not a number. That wasn't a number. Try again. Okay, so how do I try again? Yes, sir. Pardon me? Oh, that's a really clever answer. I wonder if this class will let me do it. So my dear colleague over there recommended this, but I wonder if this will scare anyone. Is it fine? So this is recursion. We're going to talk about this at the end of the year. But you're allowed to call a function from within a function. So, okay, so I'm going to leave it like this, and then I'll convert it to a while loop, if that's okay. Oh, and sorry, this should be, oh no, I have to return this actually. Yeah. Okay, I want to show you that this works, and then we'll immediately rewrite it as a while loop. Actually, I'm going to rewrite it as a while loop now. So at the end of the year, you should be able to understand something like this. It's not too bad. It's just like we're calling the function again. But let's just do a while loop instead. So while true, ask the user for an input, then try to do it. If we're successful, you can break and then return that. And if you're not successful, print that wasn't a number, try again. And then we just have to let it go through the loop. Okay, so let's give this a go. Okay, so let's call IO double. Enter an integer, 123. Enter an integer, 10. That wasn't a number, try again. 11. That wasn't a number, try again. 18, 36. Right, so you see how we've written a function that is now a little bit more tolerant to the fishy stuff that like users are doing. Like up till now, we had no way to validate input. Right, we always had to say IO double has the precondition that the user is typing in the thing that we want, which is not a sensible precondition normally to have when interacting with users. Okay, so this is how you could sort of use try catches to never have to really abort execution. Okay, so there's an answer, just so you can have it in your slides. There's another one. Okay, there's the recursion. So here's the general framework for a try except. So you try some code, and that code may throw an exception. And then you can write an arbitrary number of exceptions to say, in the event that in the code that I tried, it threw an error, in the event that it threw the error exception name 0, run this code. Otherwise run this code, otherwise run this code, otherwise run this code. But you are to never try except around everything. That is extremely bad practice. I can't sort of emphasize that enough. Okay, so here's how you raise an error instead. So finally, if you want to raise an error rather than catch it, you just use this keyword, which is not a function, it's a keyword, like return. I've been seeing a lot of people use return with braces, like this. Return isn't a function. Why can't return be a function? How does return if return's a function? Right? You're just passing the buck downstream. Return is a keyword, right? So this is something very special. So although this will work, it's because Python is interpreting it as return this, which actually, like, the brackets are just redundant. So please don't call return as a function. It just sort of looks silly, and it sort of doesn't even make sense. The same way, don't call raise as a function. It's not a function. It's a keyword. It's sort of doing a little bit different. It's like it's a keyword that you use in your functions to designate that the function is finished. So we can just go in here and I can show you how we could do that again. So I can say, okay, so let's do IO double again. But this time we're not going to do the error handling. We're just going to say, we're going to raise an error in the event that something fishy happens. Prompt user for input, prompt user for integer input, raise value error if user inputs not an integer. Okay, so I can do something like this. So first, string x is going to be an input from the user. Please enter a number. I'm going to say something like try to convert the string x to convert into an integer. And in the exception that we get a value error, I'm just going to raise a value error. This is kind of pointless. But otherwise, I'm going to return 2 times int x. Okay. So here I can do something. This is kind of pointless because this in itself is raising a value error, but it's still illustrative. So I can, and I'll do another one after this. Okay, so here I can call that in, and I can say IO double. Oops. Oops, geez, my fingers. IO double, enter a number, 7. Enter a number, IO double, enter a number, 19. Value error. Okay, so let's do another one where it's sort of not obvious. Divide. I'll do a divide. And what we're going to do is given two numbers, so I'll do something like this. I want to return 1 over x minus y. So I can say x is an integer, y is an integer. And I can do something like this. If x is equal to y, what's going to happen? We're going to raise it, like it's going to cause a division error. So here I can say raise 0 division. I think that's the right error. Oh, 0 division error here. And then otherwise, you don't throw the error. It just works. So let's try that. Okay, so divide 1 by 2. Oh, that's not, sorry. 2 by 2. That should throw a 0 division error, right? Boom. Okay, so this is a way of saying, look, you've called this function in such a way where you're going to throw a 0 division error. These errors, like raising errors, they're going to be a lot more useful once we start engaging with objects. So a safe divide like this can return a 0 division error. So in summary, and I told you the first lecture is going to be a little bit short, we can catch errors which are thrown at runtime with try-except control structures, and we should only use a try-catch when absolutely necessary. Okay, so we're going to now transition to object-oriented programming. So there are 4 modules in this course: imperative programming, object-oriented programming, GUI programming, and advanced topics. So we're more or less finished the first module. I just have to talk to you a little bit about scoping next week. Introduction to object-oriented programming is going to be important, right? Because at this school, objects, sort of like using objects is like what industry does a lot. It's sort of the standard way of programming in industrial settings, which is why you have to learn it all the year 2. Okay, so we're going to now really focus hard on objects and the types of ways that we can think about objects and the types of things that we can do with objects. First, I want to talk a little bit about interface versus implementation. So the interface of a watch is its watch face, like the thing on the left. It's a universal way of sort of communicating what time it is. The implementation of this watch is sort of the cogs and stuff that underlie it. We have to sort of have the same philosophy about creating our methods. Our methods and classes, we have to think the same way about our classes. Our classes are going to have an interface and an implementation. And the interface that we create, you shouldn't have to know anything about the implementation in order to use the interface. Like, how much did you have to know about these cogs in order to read the time? Nothing. Is it the case that if I switched out the implementation with a different equivalent, if I made this a digital watch that still had these sort of analog, like the hour hand and minute hand, except I just replaced the cogs with like a digital controller, would that affect the interface? No, but the implementation would have totally been changed. So like this is one of the important organizational strategies about using objects. You want to be able to define an interface and be able to change the implementation without screwing up everyone else's code who has ever relied on your class. Right? Because eventually you're going to be writing code for other people to use, and you won't be able to have total freedom about how you change the software that you write. Right? Because other people have written software that depends on the software that you wrote. In particular, they have written software that relies on the fact that your interface your interface will never change. Perhaps your interface will become more robust, you'll add more methods and stuff like that, but I should expect that something that your software is providing in sort of version 1 isn't going to break in version 2. Right? So we always have to think about what interface we're going to provide users of our classes, and then how we're going to implement them. This is why we don't access private variables. This is why we use setters and getters. If we didn't use setters and getters, the programmer would have to know something about our class object in order to use it, which means they would have to be sort of aware of what's happening at the implementation level of our class in order to call out. There's a MyPyTutor question about dictionaries where the analyzer probably could have given a little bit better hint. So the analyzer was trying to make sure that people were using the getter method to access the name of the friend. If you're getting some weird error messages about not returning the name of the friend, it's probably because you're utilizing or you're using a private attribute in your code. So if you're getting weird analyzer messages for your MyPyTutors, ask yourself if you're violating any of these rules that we've set up about public and private implementations or private and public class methods. Okay, so again, to summarize, we have implementation and interface. And implementation shouldn't really affect the interface. And if I wanted to change this interface, it shouldn't really, well, if I could change the interface, but then that would require a totally different implementation. Okay, so here's an example of an interface for shapes, calculating the area. So I can spin up a rectangle, and I can say it has width 1, height 4. And I can spin up a circle and say that it has radius 1. And I could provide an interface into both for calculating the area. Now, do you need to know how it's calculating the area of a rectangle in order to use it? No, that's an implementation detail. Will rectangle and circle have different implementations for this interface? Yes, but at this level, we don't care. At this level, the interface is the same, right, despite the way that it's been implemented. Polymorphism. So this is a phrase or term that we borrowed from the biologists. It means to take on many forms. Poly meaning many, morphism meaning form. So in computer science, an interface that works over different underlying classes or data type is called polymorphic. That previous example of area was technically polymorphic because it worked on a rectangle and it worked on a circle. Are there any other polymorphic sort of interfaces that you've worked with in Python? I'm sure you've used them. We'll think. Last year, this lecture went super short because there wasn't a lot of class engagement. So this year, we have to have a little bit more class engagement so I don't go short. You can't think of any operation or function that works over different types that you've used? Length. Length is a great one, right? Length will work over strings. It's going to work over lists. We could define a class for vector, and if we could define length over that. Any other ones? Print doesn't really return anything, so I don't want to talk about print. Well, what about the plus operator? So 2 plus 3 is going to be 5. Drop and bear is going to be drop bear. I really loved this when I first moved here, like this notion that a koala could just come falling out of the sky onto my face. I've lived here maybe like 5 years in total, and I'm still learning new words. Like just over the weekend, I learned 2 more. Brelly, or what's the one for umbrella? Is it Brelly or Brello or Brawly, and lollipop lady. Does anyone know what that one is? Jesus. It's not something you get from the shops. It's the person who helps you across the street. So it's still fun learning all of these things. Oh, and I learned another word for sick this morning. Crook is to be sick. I swear I could fill a book. Anyways, 2 and 3 we're adding integers. Drop and bear we're adding strings. Like the list 1, 2 and the list 3, 4 concatenates. And like I could spin up a point object and define that 2 points should be added in this manner. Right, so the point is it's the same interface. We're using the plus operation in each of these things. The implementations are obviously different. The implementation for adding 2 integers together was obviously different than the pieces of code we had to write to do list concatenation. We already went over this, but length. Length is a function that's polymorphic because it works over dictionaries, it works over strings, it works over lists, and it works over any custom class that you may define. So I can say the length of a vector is its sort of Cartesian distance, right? Or Euclidean distance on the plane. So this would be 5. 9 plus 16 is 25. Square root of that is 5, right? So, but the point is here that as programmers, we expect for some of our functions to be polymorphic. It would be super irritating if I had to have length dictionary, length string, length list, length integer, right? It's better to have a unified interface for length that we as programmers can just rely on working on different types of classes. So here's a class polymorphism, or we're going to define. So I want to move now into inheritance, right? So the name of the game for programming in general is write as little code as humanly possible. The fewer lines of code that you write, the less likely it is you're going to introduce a bug. That's kind of my philosophy. Now, after looking at some of the assignments, it seems one strategy is to just keep writing more and more and more and more code to try to like sort of control structure yourself around like weird edge cases. That's not a really good strategy, right? Because for every subsequent line, like every time you fix a mistake by not actually addressing like the key thing that's wrong, you may in fact be like making more mistakes, multiplying. So think, let's write the minimum amount of code humanly possible. And inheritance is a functionality of classes that really leans into this type of philosophy. That's really going to prevent us from having to duplicate code very much. So I want to write some code for sort of dealing with the cat and dealing with the dog. Does anyone remember Maro the cat? Yeah, you make me feel old now. He was like the original YouTube cat, right? He had like several million followers, cool cat. Bluey the dog is something that I learned about here. I'm loving Bluey. So let's make a cat and dog object for storing cat and dog and their name and their age. And let's see what kind of interface I want to provide into here. So the interface that I want to have for cat and dog is I want cats to be able to speak. I want dogs to be able to speak. And maybe I want info on the cat, and I want info on the dog. Okay, so here we have two different classes, but you can see I've defined an interface that should be polymorphic over cat and dog, right? It's an equal interface. Both cat and dog can speak. They're going to have to speak differently, and both cat and dog can get info. Their info is going to have to be a little bit different, but it looks mostly the same. So let's just go ahead and start coding this. What do I want? I want to make this bigger. Okay, so I want a class for a dog, and I want a class for a cat. So what are the things that we have to put in these classes? What's the first thing? Initializers. Okay, let's put in an initializer. Init. Where's my tab completion? Initializer, self, it takes what? Name, which is a string, and then age, which is an integer. And what does it return? None. Okay, so I have to have a little talk about this as well, because I've been doing stuff like this, returning none. Now, whenever someone's asked me, do I have to do this? My answer is always no. And I have to be honest with you. In fact, returning none is actually against the PEP 8 guideline. Now, the reason I've been including it is because no matter how much I prattle on about this, people are still printing from functions instead of returning. So I've been using this return none to be like, to make it very obvious that this function is going to return none. It's returning none on purpose. It's what we sort of call a procedure. I'm not going to do that anymore because it's really going to pollute our objects, because a lot of our objects, our object methods aren't actually going to return anything. But nonetheless, it's still appropriate to put this none back in. So I'm going to stop saying return none, but please be careful about functions that aren't returning anything. This print return difference is something that I can never resolve, right, no matter how much I try. So just keep that in mind. Okay, so what should a dog do? Maybe it should remember its own name, and it needs to remember its own age. What does cat have to do? Well, so it's basically the same initializer here, right? And the fact that it's like literally the same initializer is kind of relevant. I said we have to be, we want to write as little code as possible, and code duplication like this, literal code duplication, is like very much outside of that philosophy. So let's just see if I can go in here and just make sure that it's running properly. My call this sandbox, because again, I don't want to do too much at one time. That seems to be working. Let's see if we can get a dog object. Bluey 14. Okay, we have a dog object. So let's go back out here. What else should we be adding? So I needed two other things. We needed to speak, which returns what? I think, let's look back at the slides. So these are returning with quotes. So is this returning or is this printing? It's returning, right? If you were to print, those quotations will disappear, right? So just be mindful of that little difference. So we're going to be returning from these methods, returning a string. And so what should this do? I should return bark. Okay? How does a cat speak? So def speak self. This returns a string. Return meow. Okay? What else did we need? Some info. This is self, and this is going to return also a string, and we're going to return sort of self.name, and it's okay to call private variables from within the class because that's who gets to use these private variables or attributes. The dog is self.age old. Okay, how does this differ for cat? So I suppose I just need to change this. Yeah? Okay. So let's go in and let's see how much that we can do. So I'm going to spin up a dog. Do we now have the speak interface? Sure do. Do we now have the info interface? Sure do. Okay. So how can we now take this and make it so that we're not duplicating code? So what is something that is, like, can we look at this and see that it's like mostly the same everywhere? Okay, so this is where class inheritance starts coming into play. I want to create a superclass, a class that exists on top of dog and cat, that is going to provide similar functionality to both dog and cat, and I'm going to call this animal. And the animal is going to be inherited by dog and by cat. Right, so that's why we always had to keep putting empty brackets here. Right, this was saying, here is the list of things I would like to inherit from. The top level one, you can always put in object. Object is like the most super of all classes. Some Python programmers put it in there. I choose to omit it, right? But if you see animal object, that's just meant to indicate that, like, look, this is really at the top. This is never going to inherit from anything. It's just inheriting from object, which is the most generic type of object. Okay, so the first thing I'm going to show you is that I can define an initializer here. And in fact, I'm just going to take this out and put it here. So I'm going to take it out. And I'm going to take it out of this one too, from cat. Okay. So it's out of there and it's out of there. So I'm going to go in and show you what happens now. Reloading it. So I have removed the initializer from dog. Do you think this is going to work? No, yes? Yeah, it will work. What about the one for cat? Cat is a cat. Come on. Cat is a cat. My cat's name was Tubbs. You can be 9, right? So both dog and cat were able to be initialized. Let's do something naughty. Let's just see if, like, they actually have names, right? So don't do this in real life. I'm just doing it because for illustrative purposes. But it does seem that both dog and cat got an initializer despite not defining the initializer in either of those classes. And not only did they get the initializer, they also have use of these private attributes, this like self.name and self.age. So what we do when we're inheriting from another object, you can like consider this, it's like saying copy paste the initial code here. Right? When I say inherit from animal. So when dog inherits from animal, it says take everything that's defined in the animal class and then paste it here. It doesn't actually do that, but that's how you can sort of conceptualize it. Okay, so let's continue down this road. What other stuff can we put in the animal class to save on our sort of code duplication? I think speak we're not going to be able to put up there. Okay, let's try info. So I want to put info up there. I'll take this out. But what has to change? Dog and cat. So how are we going to handle this? Error. How can we handle it in not such a blunt way? That's the correct way. So the other piece of advice I want to give you with coding is try not to hard code stuff. Like if you can make something generic, make it generic. It's much wiser to do. So instead of having an info method that would have to hard code the name of the class in every case, we can do something a little bit more clever. So I'm going to show you a trick. I can get the type of dog, and it's going to say that I'm a class from dog. There's also, you can actually access the name by doing this. This is a little bit cheeky because we're really not supposed to be like accessing private variables, but we can if we don't really utilize them in a degenerate way. I just want to look at it. So like I'm not going to change it or anything, so this should be fine. But that's a capital case dog. How do I get a lowercase dog? Type of dog dot name dot lowercase? Is this lower? Okay. I also want to point out sort of this statement that I wrote. This statement is a very object-oriented type of statement. Rather than taking something and passing it to a function and then taking that output and passing it to another function, the way we work with objects is we take an object and we like employ a series of transformations on it. Or like I'm saying, get the dog, so everything in Python is an object, including types itself. So I'm saying get me the type of dog, which is going to be an object, which has an attribute .name, which I want to .lower. Right? So you're going to see these types of statements in object-oriented programming where you're just saying .do this, .do this, .do this. Like execute the following series of transformations. Right? And you want to be able to provide interfaces that make it easy to do something like this with your own classes. So instead of putting a question mark here, I can now put type. It's type of what? So I'll come back to that. .name, .lower. So what should go into here? Self. Okay. So this is a little bit of a nuance, right? As soon as this function gets inherited by dog, I'm saying it's as if it copy-pasted the code there. Therefore, what does self refer to? Not animal, but dog. So you're going to see that the self here is going to depend on like which class is calling it, but it's going to be inherited by both. So let's see what happens here. I can get a dog. I can get a cat. It was there somewhere. Cat is equal to cat tubs. A 9. Okay, so let's see. There is no info for dog that we put there. But we did say you should inherit info from the animal superclass. So I should be able to ask for dog.info. That's not what we expect. What did I do wrong? Oh, I forgot. See? I need to do this. Right, so this is kind of a weird bug. It's not wrong to not put those brackets there because what you're actually saying is like, give me the method. And it's saying, okay, here's the method. But I want to actually invoke the method. So you're not going to get an error. You're going to get something like this. So let's try again. But don't feel too bad because obviously I make those type of errors sometimes as well. Okay, so let's try to get dog.info. Bluey the dog is 14 years old. Cat.info. Tubbs the cat is 9 years old. So you see it was all sort of like automated. Like we really reduced the number of animals we had to, or the number of lines of code we had to do. Like for instance, if I wanted to do like another one, now we're going to get to that. Okay. Is that meme too old? I tried to calculate how old you guys would be when this meme was out. It's like 8. But, so, we'll get to it. In any case, like I could spin up a turtle, and I don't really have to do anything in it. So I can go in and I can say Yertle is a turtle. His name is Yertle. He's 101 years old. And look, this has info. Right? Like the class itself did absolutely nothing in it. But still, it has the initializer, it has the info method. Okay, before talking about the fact that turtle can't speak, let's talk about like speak in general. So I keep talking about interfaces, right? So the one way of thinking about this superclass is saying, no matter what animal you are, I want to ensure that you are providing the following interface. So you can think of the animal superclass as like a blueprint for all of the classes that are inheriting from it. So I do want all of my animals, if able, to define a speak method. Okay, but I can't figure out, there's no tricks I can play like info here to extract. There's no generic way I can determine what kind of animal is being inherited from and therefore what to return here. So in this case, it is appropriate to return an error. What error? Not implemented. Okay. So this is these are where the nuances in terms of class inheritance becomes kind of tricky, because we're able to overwrite things that we inherit. I'm going to run this just to show you that it's working. So here's my cat, here's my turtle, and I can say cat.speak, and we don't get an error. Why? Well, because cat overwrote. It said, look, inherit from the superclass, but like overwrite speak with an actual speak method. Now, what is Yertle going to do when I ask it to speak? Not implemented error, which is fine. Because perhaps we can't implement it. There is no way for a turtle to speak. Type error? Well, the exceptions must derive from base case. Oh, not implemented error. Oh, yes, now it's blue. Thank you for that. Yertle. Yeah, not implemented error. Thank you. Which is fine. Right, we're saying, look, we have this generic blueprint for classes, in this case animal, and I'm not saying that you necessarily like have to implement it, but people using things inherited from the animal class are expecting sometimes that you should be able to speak. Right? So in that case, we're going to return like a standard error. Right? So someone using this animal class or sort of subclasses of it can write now something like if turtle.speak or try turtle.speak and then catch not implemented error, right? So this still enables the programmer to have a reliable way of dealing with things that we expect animal to be providing even when they are not provided. Okay, so this is a great way to like simplify your code. Now, regards to A2, like the main drive of A2 is for you to engage with these types of inheritances and like code simplification. It may not be the best way to like implement A2. It's a little bit contrived. Like all of your assignments to some extent are a little bit contrived. So just take on the spirit of what that assignment is trying to teach you. It's trying to teach you how to engage with classes and inheritance. You may think, boy, this is sort of a little bit of a convoluted way of accomplishing this, and I agree, but it is what it is. Implement dog class, we did that. So here's, there's cat, just so you have it in your slides. There's dog. Notice both of these classes have very similar implementations of their interfaces, where it's best to reuse the code by having generic methods instead. So for example, cat and dog had identical init methods, and therefore it was overkill to copy-paste this for them and every other animal we intend to instantiate. What's the other benefit of class inheritance? Yes? Oh, okay. Right, so I suppose you're asking, can't we just maybe have like a table of all animal sounds in animal? Something like that, and then like have speak, like pull from that? Like I could, okay, so this is sort of what I'm hearing, something like, let's here have like just generically sounds, which is a dictionary, and I could say like dog goes to bark, and then cat goes to meow, and then here I could say, like, play the same trick. But I wouldn't say that's the best thing, because... okay, sorry, yeah. He's closer, so maybe you can... yeah. Oh, so instead of defining speak in this, I should define something called sound, and then the generic one calls that? Yeah, it's just, that seems to be more code than necessary. I mean, right. How? Because defining speak is two lines. If you have, this reduces it down to one for each one. Oh, you want me to define a variable called? Yes. Okay, that would be okay, but like in both instances, yeah, that would be fine as well. That would be fine as well. I prefer this, right, because it's sort of like more in line with the philosophy of providing a blueprint. It's like, here's my blueprint. Like, your class should abide by the following agreements in terms of the interface that it provides. One of the interface methods is speak, right? So either implement it or don't. Right, that would be the expectation of someone using your superclass. It would be sort of like, I agree that it's equivalent, but it would be odd behavior to describe it in the way that you want, right? To say, look, instead of defining speak, define this like other variable in the method, and like we just have to like explain a bunch of stuff that's non-standard. Although I totally agree that that would work just as well. Where was I? Okay. So sub and superclasses. So we're going to have a little bit of terminology now so we can communicate with one another. So objects are already grouped by their classes. For instance, we could instantiate many dog objects from the class dog. Like we could have Bluey the dog, Fido the dog, Lassie the dog, right? All of those instances of dog are from the dog class. So this is sort of like describing what it means to be included in a set. So in maths, we may say sort of Bluey is an element of dog. In CS, we say Bluey is a dog. So is a is sort of like synonymous with like inclusion, right? So Bluey is a dog. So we can also group classes into superclasses, right? So Bluey is a dog, but dog is an animal, right? So you can have sort of these like, we have like all the things that are dogs, and that's like a subset of all the things that are like animals, which are a subset of all the things that are objects. So just keep note that this is a relationship is somewhat important. There's two types of relationships we can have among classes. I'll flesh out this a little bit more next week. But there are is a relationships, and there are has a relationships. So this is the is a relationship. If I had created another class called person, and persons had pets, which were animals, then I would say person has a animal. Right? So that one's sort of called class composition, and this is called class inheritance. Class inheritance is more complicated than class composition. Here's an aside. So let me spin up Bluey. Is this where I just... Yep, we already done that. We have done this. We have done this. we've done this. So here's me just sort of going over like what it means to inherit. So really the way to conceptualize this is when you inherit from a class, you are just sort of telling Python, copy paste everything from there here. And the thing that you have to keep in mind is self does not refer to self of the superclass, but self of the class that I got copied into. You're also going to have access to super. We're going to get to that in a bit. So this is just me putting it in the slide so you have access to it. We went over this. What sound does a turtle make? So Yurtle the turtle is 101, Yurtle.info, Yurtle.speak. It's okay to have these not implemented errors, right? It may not be the case that everything in the blueprint is possible by every instance of that blueprint, as we see here. Here's what the fox says. So this one we could easily spin up another fox. We can easily spin up a fox class, which is a subclass of animal, simply by defining exactly one method for speaking. All right, so we did it without defining a method for speaking, and it's fine, and we did it with introducing another method for speak, and that's fine as well. But the point is, if we ever define a new animal that's a subclass of animal, we know exactly what interface it's going to provide. Right? We don't have to ask, well, how do I get what foxes speak? It's like, well, .speak, right? Because that was the blueprint that animal was giving you. And again, this is like object-oriented programming is mainly an organizational type of strategy, right? And a strategy for reducing the amount of code duplication. Okay, so again, we are able to overwrite methods by declaring them as we normally would. So if I define, maybe I should show you this, yeah. So I can go into turtle, or here, and what things have it inherited? It inherited init, it inherited info, and it inherited speak. I can go in here and just overwrite info, and I can say return turtles are better than all other animals. Okay, so let's go out, let's go in. So there's Yurtle, there's, oops, where's my cat? Cat. So if I tell, ask for info on a cat, it gets that. But now if I ask for info on Yurtle, it says, oh, that shouldn't have happened. Okay, maybe I didn't save. Save. Let's go out. Yurtle the turtle, Yurtle.info. Yeah, turtles are better than all other animals. So you're allowed to like override whatever methods that you've inherited from the superclass like this. So just keep that in mind. I'm also going to show you how to extend these things, which is different than overriding. So this is what it means to extend. Suppose I wanted the fox object to also have a nationality attribute. So this is how I could take the initializer that was copy-pasted and extend it. It's kind of like doing both. I'm saying, okay, for this fox object, please overwrite the initializer that I inherited with this initializer. And this initializer, in addition to taking name and age, is also going to take a string for nationality. And the first thing I'm going to do is just call the initializer from the superclass. Is this confusing? So that the animal class is still there, right? And I can say, what does this animal class have stored for its initializer? The thing that I'm like, usually would inherit, but this time I actually want to extend it. Right? Because we don't have access to it because I'm overriding it in this class. So I'm saying, go to the superclass, run the usual initializer method with name and age. And then after that, add another attribute for nationality and make it an extra attribute. So now here I could say Kyobi the fox, who's 1,432 years old, who is from Japan, has a name, has an age, and now has a nationality. This wouldn't have propagated to sort of dog and cat. So, oh, yes, sir.
Is there any reason to have a minute?
You got to really speak up. I'm deaf. Yeah.
Is there any reason to have a minute underscore?
Oh, I probably should have included the underscore there. Yeah. I get a little bit lazy with my private variables because that's usually something I do at the very end. I'll go and privatize everything. But yeah, this should be, I probably should have put an underscore there. I'll correct that. Now, suppose then I was like, geez, I would really like for like all of my animals to have this nationality attribute. What is one benefit of the way that we're sort of organizing our code in terms of classes here? How could I then get a nationality attribute into all of my animals? Yeah, just go to the superclass, add nationality to the initializer, and now every sort of animal is obligated to include that. So you can make changes universally across everything that's inheriting by just changing stuff in the super. Right? If you decided that like all animals like need some other type of interface, like you need, their kindness ranking, right? You just put that in one place. You put that in the superclass, and now that's something that everyone has inherited from you is now expected to like add to their implementation. UML diagrams. This stands for Unified Modeling Language. It's a diagram. This is a standard way of illustrating inheritance relationships among classes. Notice the direction of this arrow. The arrow is meant to be replaced in your head by is a, right? So this dog is a animal. This cat is a animal. This fox is a animal. As you take more programming courses, in object-oriented programming in particular, these UML diagrams are going to become super important, right? Because it's going to give you a quick visual way of looking at the blueprint that's expected for things that you inherit. This is a very, very bare bones UML diagram. Usually all of these boxes also include all of the attributes that they would be providing. But at your level, this is sufficient to sort of understand that the arrow is telling you what is inheriting from what. The has a relationship are sort of horizontal arrows. I'll go over this next week. But was there a UML diagram supplied with A2? There should have been. Okay, so that's sort of like telling you how the object relationship should be fleshing out in your code. Considering the following code snippet from the course notes, you either sort of will want to like take a picture of this or write it down because I have some questions regarding this. But it's also not too hard to remember what this object is doing. So I'm just going to contrive a class called A, and I'm saying A is as high up as you go. It's inheriting from the most generic type of object, so expect A will never inherit from anything. All this object does is store one variable, x. It has an F method that just returns x. It has a G method that doubles x. And then it has an FG method, which just returns the difference of the previous two methods. I'm going to instantiate an A object, call that A. What is A.x? These are slow balls today. Yeah, it's nice for me to have a coffee break. Do we need to go back? We're initializing with exactly one variable. It goes to self.x. So what is A.x? 3. What's A.f? 3 again. A.g? 6. And the difference between the last two things. -3. Okay, so that was pretty easy. Here's B. Let's inherit from A. And what's B going to do? Well, so here in magenta, I'm just writing the stuff that is copy-pasted. So basically everything was copy-pasted, except I'm going to overwrite G. All right, so B is going to do all the same stuff that A was doing, except its G is going to square. So that whole class actually is equivalent to just writing that. Right? Again, this is one of the advantages of the inheritance in the first place. Like I went from something that was 12 lines of code to something that was 3 lines of code. So I'm going to instantiate a B object. I'm going to initialize it with 7. What is B.x? What is B.f? What is B.g? 49, right? Because again, this self refers to this B and not the self of the superclass that we inherited from. And what is the difference between 7 and 49? -42. Okay. We are now going to inherit from B, which is itself inheriting from A. So let's try to go through this. So here's the class C. And in C, I'm going to inherit from B, which is itself inheriting from A. And in C, I'm going to extend the initializer rather than override it. And I'm going to extend this FG method instead of overriding it. So this here says I'm extending from B, from A, this initializer method. So I'm calling what B is doing to super, and then having another attribute. So in effect, what does this call do in this class here? So what was the initializer doing in B? Or what was the initializer doing in A? It was just setting exactly one input x to the input. Okay, so B inherited from A, and it didn't override its initializer. So in effect, this call is just saying self.x is equal to x in sort of a very roundabout way. Yes? Then this super would be doing what B is doing. Then you get super.super in it, right? Right? You go two times up, which is also possible, right? When you call super, it's saying, give me the thing that I'm a direct, that I directly inherited from. But super itself is also going to be a class object. So you could ask, what's the super of super? And eventually, what are you going to get? If I keep calling super.super.super.super, this has like a fixed point. I hope. Do you guys know what a fixed point is? When you give a function a variable, and it just gives you back that variable. Okay, who cares? I'm going to keep calling super. What happens if I called super 100 times here? Well, huh? But what is the top level? No. What is super of A? Object. And what is super of object? Object. Right? So eventually you're just going to hit the top, and it's going to say you can't go any further than this. I'm actually not sure that object has a super. Let's check. Object.super. I'll have to get back to you on that one. I wouldn't actually know how to. I perhaps have to do this in the class itself. Let me think about that one, and I'll try to get something on the EdStem. Huh? We'll handle it later. Okay, so we have this is basically saying self.x is equal to x. We're extending it by adding one more class attribute, calling it y. And what's this going to do? This is going to call the super f.g, which is the thing happening in G, which we have to be careful about because super, okay, so I think it's better. I think I actually have this copied out now. Because we're going to have, it gets, so the reason I'm showing you this is because like a question like this shows up on every single final in this class for like the history of this class. And in fact, like the final task I'm going to have you do today is like the inheritance question from the exam last year. And it always is sort of like this. So we're looking at C. So let's just see what I want C to do. Okay, so we're going to say the C object is 3, 5. Okay, so I need to go get a different file now, A, B, C, D. We're going to try to work this out. I'm going to create this. I should probably have called that C. And what are the things that I want to know? Okay, so let's just go through all of the attributes and methods that C has. So what should C.x be? I think it should be 3. What about C.y? 5. What about C.f? So C.f, that was a function that was inherited from B. So B's f is actually the thing inherited from A, which is just returning itself, 3. Okay. What about C.g? Okay, so is there a G in C? Well, not explicit. Okay, am I overriding the definition of G in C? No. So where should I look for the definition? Okay, so we go look for B. And B did inherit a G from A, but actually it overrode it. Okay, so actually C has this as its G. So what should C.g be here? Self.x squared, right? 9, okay? finally, what should C dot F of G be? So let's look at what's happening here. Oh, why is this there? Okay, I need to return super.fg. So what's super.fg? So that is saying, look to B for its super. Well, that was actually called from here. So it's sort of like, it's as if I'm using this call here. Okay, so this is going to be the difference between C.F and C.G, which is what? So here's C.F, here's C.G. Their difference should be, so this should be minus 6 times self of y. Self of y was what, 9? I have a feeling I did this wrong. So minus 6 times 9 is minus 54? No. Something, oh, that's why I printed here. So we could know what super.f of g did. So which one did I get wrong? Oh, sorry. Yeah, it's not, c.y isn't 9, it's 5. So this I calculated correctly. That's minus 6. I calculated incorrectly. That should have been 5. So this is minus 30. Okay? But this stuff, it gets sort of, you got to be really careful when you're like sort of working with these class inheritance types of question. Okay, so there's all of that. Method resolution order. So I'm going to do one more thing here. I'm going to say, let's create a class D, and I'm going to overwrite F and return this. So this is kind of tricky, right? Because like, what self does this self refer to? What G is this referring to? Yes, miss? You can inherit from multiple classes. Well, because like there's an implied order, like you're going to have to write eventually like there's no way of telling Python like inherit simultaneously from these two things. Like you're either going to have to do like two inheritances, one after the other, or in like the class inheritance, you're going to have to like say inherit from A and then B. And then it just becomes like saying, well, we can either say the last thing will always overwrite or like the first thing will overwrite. So like that, again, like that's the principle you have to have in your mind. When we inherit, it's just like copy pasting it. And then when you inherit from multiple classes, like it's sort of like an arrow that like does this, you just say, well, the last thing that technically you inherit from will overwrite the first thing that I inherited from. Let's not worry too much about like what it means to inherit from multiple classes, because I just want to focus on like grappling with inheritance to begin with. But that's a good and natural question to ask. Maybe I'll follow up on that next week. Right, okay, so what is D? How about now? My name's Paul, not Philip. Okay, sorry about that. We'll go back. So I think we lost the chat at D. Okay, so the purpose of this example was just to emphasize that, like, just be careful about, these super and selves. Like, the self always refers to the object that inherited. Super is going to refer to the class that you inherited from, and you can go up the chain, right? So if you've inherited from something that inherited, that is something that is totally fine. So here's the answer to that. And then here's the UML diagram for sort of this contrived example, right? So we had a superclass A, both B and D were A's, or is A, and C is a B, which is a, right? So this is just a very simple class. You just got to be careful about how you're resolving things. Okay, so there's two things that I want to finish off with today. I want to implement some classes for shape that have the following interface, and then I want you to solve the exam question from last year that dealt with inheritance. So I was having trouble thinking of like what type of interfaces that shape can have. This is not going to be the greatest example because area, circumference, and number of sides are going to have to be implemented by every instance of shape And there's no way that we're going to be able to make it generic. However, the purpose of this, I guess in some sense, is not really like, it's not always about reducing the amount of code. It's about defining the blueprint or defining our expectations in terms of interface. Remember, at the beginning of class, I was prattling on about how important it was to have interface and implementation. So at this level, like without even really writing any code, I'm saying, okay, we're going to have shapes, and these shapes have to provide the interface for area, circumference, and number of sides. Because now if I said, okay, I'm going to sort of have an instance of shape called circle, and I could say, how do we get the circle's area? Well, circle.area, right? We don't care about how it's implemented, but already, just by looking at this blueprint, we can predict how anything that inherits from this is going to behave, right? So that's sort of the benefit. So let's just go out, and I'll implement that. And then if you can think of anything else that we should be able to, like any other interfaces on shapes that could be useful, let me know. Okay, so we're going to define a class for shapes. Let's make it a top-level object. We always need an initializer. And I lost my auto-completion. Initializer which takes self, and, well, I don't know yet, but it certainly returns none. And then let's raise not implemented error. Not implemented. Jeez. It's really tough doing this without the auto-completion. Okay, what was it again? Not implemented error? Perfect. Okay. What else did I want? I also wanted area. So that has to take self. This has to be none. And we're just going to say also not implemented. Number of sides. Maybe that takes self and returns integer. Whoops, integer. Also not implemented. Def. So it was area, number of sides, and circumference. Circumference. Self. And that returns float, I suppose. Yeah, area should also return float. This is going to raise a not implemented error. Okay, can we think of like some stuff that sort of like could be generic at this level? Perimeter? Is that the same thing as circumference? Oh, so I should change this with perimeter? Perimeter, sure. I don't think perimeter, though, could be... That would be tough to make perimeter generic. I think I would need I need at least one more piece of information, side length. Right? Because if we had number of sides and we had side length, then maybe we could get this. But even then, that's presuming that all like the sides are equal. So I'm just going to leave it like this. But perhaps we could have... So remember that we have these representations, these magic methods, these dunder methods. This should return a string. Perhaps this is something that we could sort of make generic. Maybe I can say for the string that this is return sort of, let me see, playing the same trick, self dot type of self dot name dot lower the shape. Okay, so all of our shapes, no matter what we call them, are going to be able to like have a string representation that says circle the shape, or maybe I am square the shape. Okay, so let's do some of the implementations for the inheritance now. So let's have a class maybe for a rectangle. That shouldn't be too bad. This is going to inherit from shapes. So we are just going to we're going to have to define everything, unfortunately. So let's get an initializer. And what things do we need to initialize a rectangle with? Pardon me? Length and width. That sounds great. Length. That should be an integer. Width. That should be an integer. And it returns none. And maybe we just say self dot length is equal to length. Self dot width is equal to width. Okay. What else should we do? Maybe it's area. Self float. And this is going to return what? Return self dot length times self dot width. What's its number of sides? I think, yeah, that's basically just returned 4. And then we don't have to define, oh, perimeter. What's the definition of the perimeter here? I think that ended up being float. How do I get the perimeter? Yeah, so it's just 2 times, I guess, self dot length plus self dot width. Okay, so we weren't able to save much. Let's just go out and ensure this is working. Great, let's see if I can get a rectangle. Rectangle 1010 or 1015. Did I spell rectangle wrong? Did I do something wrong? Okay, there's a bunch of stuff here. So, okay, one thing at a time. Let me just check. So I'm on the desktop. There should be sandbox. Box. Okay, that's better. Errors are better than not knowing why nothing's working. Object is not defined. What? Okay. Oh, lowercase o. That doesn't seem right. Oh, okay. Because normally our classes are obligated to be uppercase letters, so that's sort of a... I'm just going to remove it. I'll have to double back on that. It's tough teaching something that changes every year. Like I teach calculus too, or used to, and that doesn't change. That's nice. Okay, so let's get a rectangle. So I should be able to get rectangle that area now. Perfect. Okay, so we weren't able to sort of utilize shapes here. Now, I'm saying maybe we can be clever. What happens if I want to have like a class for square? How can I be clever about code duplication here? Yeah, I want to inherit from rectangle. What do I want to inherit from rectangle? Basically everything, with the exception of what? Well, the initializer, right? So I'm just going to overwrite the initializer because I just need to take a single length attribute. And what should the initializer do? Exactly. I want to call from super its initializer and just put length in twice. Length. Oh, geez, not like that. Not like this. Length and length. Is there anything else I think that I would have to do? Yeah, it seems that like this is really going to give me a full implementation for square, right? Just by instantiating a rectangle that had width and length equal to itself. Width and length are the same. I should have called it height and length. Anyways, so let's try going out. Let's see. Whoops. Line 33. What did I do? Oh, comma. Okay, so let's see if we can get a square. And that should be 10. So can I get its area? Perfect. Can I get the number of sides? Perfect. Can I get its perimeter? No, because it's broken? Well, I can get its perimeter. Okay, so it's very broken. Okay, let's fix all of this. I'm going to call this peri. And then 2 times... Which one's wrong here? Okay. Oh, I inverted this. Perfect. Okay, thank you. So let's try again. So there's my square. There's my perimeter. Perfect. And like I can even get like these string representations. I am square the shape, right? So this is sort of how you need to start thinking when dealing with objects. Like not to both have defined square and rectangle, right? Because that is code duplication. What should I implement instead of circle? Ellipse, right? Because like having all the stuff for ellipse will give me circle. Suppose I wanted to start representing polygons. Well, I probably could have some type of n-gon class, which everything else can derive from. So like I know this seems like a trivial example, but you could really like take this example and make it way more complicated. So it's very worth it to think, what are the most fundamental objects here? And what objects, if you like have a bunch of objects and you start noticing that they're providing the exact same interfaces, you should start thinking, is it more appropriate for me to like store this or like have code inheritance, right? So again, that's the driving force of A2. There's just, okay, so I have a question for you to do when you leave. So just in summary, classes are further categorized into superclasses which provide abstract methods, which a gentleman over there was asking me about this. So the methods in the superclass are called abstract, right? Because they're the blueprint that we're trying to enforce all inherited objects to have. Next week, we're going to start talking about GUIs. I'm going to talk a little bit more about classes because we have to flesh out this has-a-is-a relationship. Oh, I used to have some slides about common mistakes, but that must have been out last year. Okay, so what we're going to do now is I want you to work through the exam question from last year. Of course, you can leave if you want. So I'm going to put this up here. I wonder if is this too small or can you see it? All right, I'll try to figure out something to do. Okay, so if you want to leave, go ahead. I'm actually going to stop the recording.